hitting the highlights of energy. And so up here are some types of energy. You may have heard of some of these terms. But the thing about energy is we can track energy. And we can track it because it's got to be conserved. We talked on Wednesday about conservation of momentum. Straight momentum or angular momentum, got to be conserved, got to be tracked. So also energy, it's got to be tracked. It's kind of nice. It's kind of, oh, that makes sense sort of thing. Okay. So you kind of see the arrows going back and forth between these different types of energy. We get, the sun sends us, we're going to talk actually on Monday, when we kind of ease into Unit 2 in Chapter 5, we're going to talk about the sun sending energy. The sun gives us sunlight. The sun also sends us ultraviolet radiation, which we protect ourselves from using sunscreen. The sun also sends us gamma rays, like the Hulk sort of gamma rays. Okay, but gamma rays would basically kill us, but the Earth's atmosphere protects us from that. Okay, so that's radiative energy. Light is one type of radiative energy. Kinetic energy is the energy associated with motion. Let's you see the bicyclists up there. Okay, the bicyclists consume candy bars, etc. Okay, they turn via chemical energy that candy bar into muscle energy that the muscle can use. Okay, and then that muscle turns it into kinetic energy. So they're all kind of go back and forth. But you should be able to kind of track it. So energy can be conserved, and it must be conserved. Energy can't be created or destroyed. I'm going to give you an exception to that. It can't be created or destroyed, but energy can go back and forth between matter. Sounds almost like science fiction, but it's true. Energy, like we saw on the previous slide, it can be swapped, it can change forms, etc. Okay, so this here is a little off too, this third bullet on my slides. Okay, you know the universe is expanding, right? And if you take that expansion back in time, like rewind it, okay, if it's expanding now, it must have come from a single point. And that point was where the universe originated from years and years and years ago, about 13.7 billion years ago. And the energy that was associated with that event, okay, called the Big Bang, actually needs to be accounted for in what we have in our universe today. Not just the energy, but the matter we have in our universe. Okay, so one type of energy is thermal energy. Probably use a thermometer to kind of gauge the thermal energy of an object. But I'm going to show you that it's not just the thermometer that says how much thermal energy an object has. In order to understand thermal energy or heat, okay, you need to know that all matter is moving. In chemistry, which is my native, it's one of my degrees in, but in chemistry we count on the fact that all matter is moving. And can kind of see the motion of that matter in that box? So if we jack up the temperature, what do you think the longer arrows are indicating? Moving faster, exactly. So kind of from left to right, we have a cooler temperature and a warmer temperature. So we could put our thermometers in these. We could kind of have an imaginary thermometer, and this one would read cooler, and this one would read warmer. So all matter has motion, and that motion is one of two things to say how much thermal energy an object has. So speaking of thermometers, I'm going to introduce you, well, you probably are familiar with these ways that thermometers give temperature. So there's the Fahrenheit scale. It's called the English scale. And looking at water, okay, on the English scale, we would say water freezes at 32 Fahrenheit and it boils at 212 Fahrenheit. Okay? Right. The Celsius scale, okay, the Celsius scale is metric. And Celsius scale makes a little more sense, I think. Again, it takes water, which is so important to us here, and it says water will freeze at 0 Celsius and water will boil at 100 Celsius. Okay, so that is a metric way of looking at the temperature. The last one, and actually we'll be talking a little bit about this in astronomy, is a scale. It's also metric. So kind of as I draw kind of a relationship between the Celsius and the Kelvin scale, you're going to see a connection. These are both metric, So let's look at those important points of water. On the Kelvin scale, we say that water freezes at 273. We say that water boils at 373. What's the difference between 273 and 373? 100 units, exactly. 100 units. Kelvin units. What's the difference between the temperature at which, on the Celsius scale? Also 100. The temperature at which water freezes and which water boils on the Celsius scale, also 100 units. That red makes me think of blood, like units of blood, but it's not units. Okay, 100 degrees Celsius, 100 units Kelvin. They're both metric. So this is the cool thing about those two, and it kind of makes it kind of easier to go back and forth. The unit on the Celsius scale is equal to a unit on the Kelvin scale. They're like lock and step because they're both metric.
1 and 1.
They're 1 and 1 unit. So they're like offset. The one other thing, and it has to do with the fact that all matter is in motion, I think you probably see on the next slide, is that there's this important point on especially the Kelvin scale called 0 Kelvin. At 0 Kelvin, all motion stops. When I say motion, I'm talking about molecules and atoms. Okay, at 0 Kelvin, all motion stops. We call that absolute zero. Okay, and so if I told you all matter has motion, and if motion stops, it's kind of one of those conundrums, right? You have just violated a law of your universe. All matter has motion, motion stopped. Wait, which is right? Okay. So the thing is they can make things colder and colder. So if I was doing this, okay, this is warm, this is cooler, this is cooler, this is absolute zero. Okay, you can't get something that cold. Temperatures in outer space, like Pluto, the dwarf planet Pluto, right? It's got some kind of temperature zones on its surface. And New Horizons is on its way, July 2015, be out there. But Pluto runs, I think I've read, 5 Kelvin and 7 Kelvin, depending upon what part of Pluto you're on. So, you know.
That's pretty cool.
That's still pretty cold, yeah. Yeah. So, the 3 temperature scales. Oops, did you need something there? Oh, sorry, yeah. There I have it at the bottom. At absolute zero, all motion stops. All right. Okay. So, when we talk about how much thermal energy an object has, you see how I'm kind of holding my arms out here? Okay. The amount of stuff that you're pointing at to say how much thermal energy it has, that makes a difference. And I'll kind of show you an example. We have 2 examples here. We have a pot of water at 212 Fahrenheit, so it's right at the boiling point temperature. And then we have an oven with gas. So these are like kitchen things. And it's at a higher temperature, 400 degrees Fahrenheit. So what this caption says is those bodies of stuff, the boiling water and the hot gas, they both have the same amount of thermal energy. And you'd be like, well, my thermometer says higher here. Or sorry, my thermometer says higher over here. Okay, but it's more sparse. It's less dense. Okay? Higher temperature, but it's more sparse, less dense. This says, oh, my thermometer says a lower temperature. How can that have the same amount of thermal energy as my gas? Well, because it's more dense, it's more compact. It's got the lower temperature, but it's more dense. So you could stick your thermometer and stuff and get a sense, whenever you stick your thermometer in something, you are getting a sense of what kinetic energy that matter has. Okay? But in order to fully describe how much energy, thermal energy it has, you've got to take into consideration its density or its mass. All right. So I'm going to look at a couple different looks at potential energy. A lot of times people will kind of pair up kinetic energy, motion, and potential energy. Potential energy is what we call stored energy. A lot of times they kind of go yin and yang, kinetic and potential. So if you have the potential to do something, that means you could do something, but you're not doing it. Okay. So one look at potential energy, and actually the both looks at potential energy is going to be the energy associated with gravity. So to kind of focus on what I'm trying to describe, let's just picture, let's not worry about the throwing up part, the guy throwing it up or girl throwing it up part. Let's look at the falling part. Oh, I did that again. See, that was me too. Oh, well. Let's look at the falling part. We talked about this on so long ago on Wednesday, okay? And we said that this is the Earth's surface down here, or the middle of the Earth down here, actually, and it's going to fall, and it's going to go faster and faster, right? According to little g, acceleration. What's the value for g? It is 9.8. I like 9.8 or I like 10. Very good. And the units are meters per second squared. Yep, meters per second. That's a speed, meters per second. And what acceleration is increasing speed. And it's going to increase 9 meters per second for every 1 second it falls. So that's why 9.8 meters per second squared. Per second. So for this part over here, do you guys buy it's going to fall faster? It's going to accelerate. How fast is it going up here? The very top. It's not. That's right. Very good. Right at the very top, it has, I'm going to put its velocity is equal to 0. So how much kinetic energy does it have at the top? None. Exactly. No, and I'll go ahead and abbreviate it KE. No kinetic energy. Cool. But it could fall. And that's what we mean by potential energy. So it basically has no kinetic energy, but it has lots of potential energy. So I'm going to say PE equals lots. We could quantify that based upon how high it is. All right. So back to the figure. So at the top, no kinetic energy, lots of potential energy. Okay. What about the bottom? Right before it splats. Does it have much motion? It has the max amount of motion it's going to have. So it has lots of kinetic energy. When it, centimeters before it hits the ground, does it have very far to fall? No. So that's why it says down here it has, with regard to potential energy, it just says less. I would argue has very little potential energy and lots of kinetic energy. So it kind of swaps back and forth. And you could have taken a midpoint here where you say, oh, it has a moderate amount of space it can fall, moderate amount of potential energy, and it's going moderately fast. So it has both. They swap. Energy is converted from potential energy to kinetic energy. Okay? All right. So another thing about gravity. It's probably a little more nebulous. No pun intended. But does this look like, can you guys see the cloud here? When we talk about our system of a sun and the planets, we're actually going to talk about something called the solar nebula. And the solar nebula is just kind of a dust cloud that ultimately birthed our sun and the planets. So does this look kind of the same throughout? That's another cool thing about our sun and the planets. It started out as the same stuff, okay? It's just which you think has more stuff, the star, our sun, or the planets? The planets seem like they have more stuff because you stand on them. And what we find out is that the sun has the lion's share of all of the mass of this cloud, the original cloud. The sun, yep. The sun basically grabbed it all. And the planets, even Jupiter's humongous. Even Jupiter's kind of like, doesn't have much mass of the original blah. Okay, so we're going to talk about how actually this ended up being our solar system. So the thing about it is when the cloud was out like this, it had a lot of what we call gravitational potential. It's kind of like that thing above that ball that can fall. This, it has a lot of gravitational potential. And when we talk about our solar system being into the form that we know it today, we're going to see how that cloud fell in, okay? Actually, our star, in order for any star to get planets like our star does, it not only needs to come in on itself. Do you see where it's smaller there? But it also needs to be spinning. You need to get a little bit of a spin here. And just like that skater, she went faster when she did this, okay? So, because her spin was conserved. So also when that cloud that is going to birth our solar system came in, it spun faster and faster and faster. Does that look like the plane of the ecliptic there? Yeah, I think so too. So in this case, like this slide says, that potential energy moved into a kinetic energy, actually heating up that matter. One of the things that stars need to overcome before they can go ahead and begin shining on their own is they're too hot. They need to cool down, okay? Because they just do. It's one of the stages of a star being born. And it's kind of neat because we can see stars being protostars, being too hot to turn on, cooling down, and eventually turning on. So that's kind of fun too. Okay, so energy is conserved. Did you get all those little, called Waldos? But it goes from gravitational potential energy to thermal energy. You could argue kinetic energy too. Okay. So I said all energy needs to be conserved, and I said, well, kind of. What Einstein came up with was basically the formula that we use today for our nuclear power plants. We also use this formula for our nuclear weapons. I'll put this whole slide up here, unfortunately. So according to Einstein, you can, and we do, and stars do it all the time, it is possible to take a little bit of mass, like the slide says, just a little bit, and make lots of energy. And the reason we get a little bit of mass makes lots of energy is this C term right there. What does C stand for? What's the variable for?
Speed of light.
It is the speed of light.
Well, why isn't it us?
Why isn't it what? Oh, I
Isn't it
know.
L or, you know.
That's a good question. Maybe it's Latin.
Why is it E? or
Why is,
T?
yeah. Why is it the variable C? It is. That's a real good question.
I'm going to be C
A lot of things got named because of Latin.
with their Latin
Yeah.
original names.
Yeah. So I'd have to track it down. But so you can go back and forth just to kind of simplify this to kind of how I think of it. You can go back and forth between energy and you can create M being matter, and you can take matter and create energy. Okay? Matter creating energy, that is, I'll go ahead under that bottom arrow, put nuclear reaction. Nuclear. I'll put RXN for reaction. Energy going to form matter. That's almost like a Star Trek, like a transporter thing to me. I don't know. You take your matter, you turn it into energy, and then you take the energy and turn it back into matter again. Meantime, you transport, you stream that energy somewhere else. Yeah, you can quote me on that. But the thing about the energy going to form matter, I'll just go ahead and put Big Bang up here. And it won't be clear until the snow's probably flying that we get to the subject of the Big Bang. But at the time of our initial unfolding of the universe, there was lots and lots and lots and lots of energy. And there was no matter. No matter, there's no matter. It was just pure energy, just kind of like you see the science fiction movies talk about. Just pure, I said matter, I'm sorry, just pure energy, just pure energy. Okay? And so very quickly, some matter was created out of all that energy, according to this relationship. I just think that's cool. Okay, last topic. There's just a couple topics here. And this makes it hard to kind of talk about this idea of tides, because for tides to make sense, you need to have, the way I'm going to talk about it, a large body of water. And the Mississippi and the Des Moines River don't really have tides, okay? I guess in one reason they don't have tides is because they're always moving. But picture a large body of water, one of the oceans, and the oceans actually, it's a gravity thing. The oceans actually are attracted to the moon. Do you see them like lifting up and being attracted to the moon? Just the oceans. Okay, but the side that's towards the moon is attracted, and the opposite side is swung out too. Okay, so just to kind of orient yourself, what is that location at the top of the Earth right there?
Like where you put your thingy?
Yeah, where I put the red.
Well, it's gonna be up above Canada.
Right, up above Canada,
Right
exactly.
above,
We're looking
Alaska.
down. Yeah.
I don't know what ocean that would be.
No, that's
That's what you're asking.
no,
No, I got
no.
it.
But I'm gonna put North Pole.
North Pole.
Exactly, that's what I was after. So we're looking down at the Earth here, okay? And of course we know that the moon orbits the Earth going counterclockwise, okay? But the Earth completes one rotation every, how long does that take? 24 hours, exactly. Okay, so here's the deal. The Earth is spinning on around that dot every 24 hours. So we have a high tide here. I'm going to put high tide. Looks like a high tide, right? Okay, and that kind of, underneath that kind of bubble, the Earth is spinning. And do you see where we're going to have a high tide, shown anyway, over here too? Another high tide. How many hours are between those two high tides?
12.
About 12. Very good. That was my point. So you basically get two high tides 12 hours apart. And it's kind of fun on the internet. You can, I know we don't care about tides much, but tides are, if you've ever gone to like the ocean and picked up seashells, okay, you're counting on the water recessing, okay, going out when it's not near facing the moon, and the water coming up when that location is kind of on the side of the moon. Now, I kind of didn't show it, but there's a lag time. There's like a 10-degree lag time, I think. I think the bulge kind of lags behind where the moon is. But I think that's cool. So there's just a few twists to this whole thing. I guess the biggest player to make the twist is the sun. Okay, so when I was up here the other day, you know, and we made this the sun, and we can make the podium the Earth, and I'll be the moon. We talked about phases of the moon. Okay. And like, for instance, what phase is this if I'm the moon? And that's the Earth, and that's the sun. What phase is this if I'm the moon, and that is the Earth? And I'm going to kind of go around here. But I got here. You see the whole half of the moon, exactly. So what phase do we call that? I heard someone say full moon. It's a full moon. You see the full disk. Yeah, exactly. So another week goes here. What phase of the moon is this? Sorry. I'm kind of making a right angle with the sun and the Earth. It's a quarter. You see half of the moon. Exactly. We call it a quarter. How about here? Where's the illuminated side? Back here. It's 0. Right. New moon. Perfect. And so the sun over there, if it's lined up with the moon, like here at new moon, it can do an extra pull with regard to gravity. So we have, do you see the word spring up there? This is called a spring tide. And so as the Earth spins, 24 hours, it'll have every 12 hours it'll have high tides, but it'll be especially high. It's called spring tide. Okay? And about 2 weeks later, right, because it takes about a week to go a quarter. So about 2 weeks later, we're kind of between new moon and full moon. We got the whole lined up thing again. So the sun kind of gives an extra bing to the tides, called the spring tide. Well, if we go ahead and make the moon at a place in its orbit about the Earth where it makes a 90-degree angle with the sun, okay? So what phase of the moon is this? Quarter, first quarter, very good. Here and third or last quarter, okay, the sun's trying to go ahead and do its thing, okay, with regard to gravity, and it's fighting directly against what the moon wants to do with regard to tides. Okay, so it's a diminished sort of tide. So at both quarters, you get what we call a neap tide, kind of a diminished or less tide. Okay. All right. Last couple of topics. It's a classic that if you go to a planetarium, they will, and it might make little kids cry, but they'll say, the moon is moving away from the Earth. And it's true. The moon has been slowly getting farther from the Earth ever since they were kind of a couple. Okay, nothing personal. And I kind of think of it as sort of like a torque sort of deal. Oops. Let me go back to, I guess I want to do this one. I mentioned that kind of the bulge is a little bit behind where the moon is, and it kind of has consequences of flinging the moon away. Okay, so little by little it's spiraling outward, and it used to be closer. The last thing to talk about is this one. Now, she's doing what I was doing, but notice when I was doing it just a minute ago, I was trying to kind of keep my facing towards, as I was the moon, I was trying to face towards the Earth. And you guys on your homework called this synchronous rotation, and this is why we only see one side of the moon, the near side and the far side. But here, do you see where she's not doing that? Yeah. And over time, like this says, it actually over time, since these guys have been a couple, that's kind of fun, right? Since the Earth and the moon have been paired, over time, just eventually, it got what we call tidally locked. It was a relationship sort of thing. The moon used to kind of do this, okay? Extreme, kind of see it over here. Dizzy, okay? But eventually, as it actually was interacting with the Earth, it kind of calmed down, settled in to what we know it today, and we only see one side. So years ago, like hundreds of thousands of years ago, we wouldn't just see one side. Okay, but the tides locked it. We see this same, there are other planets out there like the Earth that have moons orbiting them, and we see this tidal lock over time too. Okay, I think that's it. Put the last Waldo up there. So these usually would be due the next time that we lecture, but I'm going to go ahead, and I said they'd be due when you come to take your test on Wednesday, and I'm going to stick with that. Okay, but Monday, be sure to print out Chapter 5, because we're going to start in on Chapter 5, even though it will be for your next unit exam.
Miss Knight,
Mm-hmm.
I tried to go through to get caught up from when I missed Wednesday.